From ContainerDays Hamburg, this video is proudly presented by DAX-IT.
So a bit of a backstory that session. I delivered another talk about node problem detector a couple of years ago at KCD Austria. I don't know, how many of you know node problem detector? Couple of you. So I was really amazed by this ability of just being able to surface kernel issue or Linux system issue and make things bubble up into the Kubernetes API and applying things like no schedule kind of taint to Kubernetes. So I thought maybe I should try to do it myself with more maybe modern tools and play out with eBPF and start explaining why you may want to use eBPF versus Matrix API versus Prometheus, all these kind of things. So I've packed all of my experiments into this session, so hopefully it's going to be useful. So we're going to be tackling a lot of different topics around observability, around eBPF, BPF trace. So hopefully everyone knows about eBPF. Yeah, for people who doesn't raise their hand, they're probably living in Iraq for the last couple of years. Anyway, so let's get started. So my name is Nic Vermande. I've been working for about 8 years now on different aspects of Kubernetes in engineering, product management, developer advocacy. I've been working on CNI, so networking, storage, edge, security. My thing, I really enjoy coding, fun apps. I code for fun, not as part of a big team, which sometimes I find it a bit boring. Like always the same code base. But I love coding. I love experimenting. I'm a tinkerer. And especially I love to code tools. So right now I'm a DevRel at ScaleUp. So quick 30-second on ScaleUp. So what do we do at ScaleUp? Like shameless plug. So ScaleUp is just a resource automation platform that continuously optimizes your workload resources. And it's a single platform for all the multi-dimensional scaling you can think of, like horizontal, vertical infrastructure, with the goal of improving performance, stability of the cluster, and of course, reducing costs. Right? That's for the marketing part. And if you want to connect with me, you can do that over LinkedIn, but also I'm a very avid distance runner. So my preferred social network is probably Strava. So if you want to connect on Strava, that would be the best place to connect with me. All right, so a quick agenda for today. First, we're going to take a quick look at how Kubernetes can sometimes hide metrics with the default observability tools you have out of the box. Then, still with this NPD kind of mindset, I wanted to go to two different directions. So first, how you can sort of eavesdrop what Kubernetes is doing, for example, when creating a pod, what's happening at the kernel level, and how to monitor that. So that would be also a good excuse to kind of do a quick refresher on what happens when you create a container in Kubernetes or pod. Then again, the other direction, so similar to NPD, where we're going to take a look especially at what happens when you have things like CPU throttling, how to monitor that, and how to get the right information. And again, how it can differ from what Kubernetes is telling you. And so finally, we're going to take a look at the solution I've built using eBPF, which is based on daemon sets, operator. So we're going to touch on also this pattern, which is if you want to create a sort of custom solution, so using eBPF or another observability tool, something a bit custom, and you need custom resources, operators, we're going to take a look at that, and hopefully you will have some good information. So hopefully sounds like a good plan. You should not sleep. I guess it's packed. So let's move forward. First thing, so probably everyone has already used that command, kubectl top, which gives you, for example, here, 96 mil CPU, 178 mega for memory. So it's based on the metric server, right? So which provide a default in-memory cache of core metrics for the API server, right? So it's mainly aggregated, so you can't necessarily have a long, historical data, and we're going to see that, that's probably why you want to use something like Prometheus. So for deep, long-term observability and advanced, auto-scaling, then Prometheus plugs in via an adapter to feed the custom metrics API, so register with the custom metric API to essentially give you metrics and visibility on what the default metrics API or the metrics server basically cannot do. And typically, this is what you will see in Grafana, right? You don't see the metrics server directly in Grafana. You will have to go through custom metrics API and use something like Prometheus. So it will give you some sort of visualization for rich historical database. But again, here with the same, it's basically the same thing as before, but represented into your Grafana. So just looking at that, everything seems all right. So this is part of the solution I've built that I'm going to show you a bit later. So by using something like eBPF, and more particularly eBPF trace in our case, I've built this custom resource that not only tells you like the same thing, so essentially, taking a look at the CPU usage. This is this 225 that we have here. This is just an example. So imagine we have this 285 CPU usage, and then we can also, gather from the container manifest, or the pod manifest, should I say, not the container part, the limits and request for it. But then what is really missing is the CPU demand, right? So if everything is fine, you should have CPU demand equal CPU usage. But what happens if you reach your limit, right? So this is where you start to have CPU throttle, right? So do not mix this up when the host is, like the CPU resource as a resource is scarce on the host, and is just basically posing container operation. Throttling is very specific to CPU limits. So if you don't have limits on a container, you won't have CPU throttling. So that's, I wanted to first mention that. So here, the idea is to gather via an observability tool the throttle percentage. As you do that, if you divide the CPU usage by the percentage of when the container is not throttled, so basically 1 minus the throttle percent, which is 75 in our case, so 0.75. So if you divide 300 by 0.75, normally you should get 380, right? So which is exactly what the container demands, but it's not what it's getting. So you think that, okay, my CPU usage is 285. I'm a bit below my limits or resource or request, so it may look healthy, but in reality, if you're missing the context, right, the CPU throttling and the CPU demand, then you will never know that your container is actually not really healthy, right? So this is why I'm saying Kubernetes is lying to you, right? So that was for the introduction. So now let's focus on, if we are creating a container or a pod in Kubernetes, here in that particular instance, a container, what is really happening in the kernel, right? So probably everyone is already familiar with the different namespaces. So first, of course, creating a container is a set of syscalls, and all the syscalls belong to different sections here that are meant to do different things. So for the first thing is when you create a container, the system is going to create multiple namespaces. So we have the PID namespace, which is isolating the process tree. Then you have UTS namespace, which is not time, but it's just the container host name. We have the IPC namespace for the inter-process namespace. We have the mount namespace, the network namespace, the user namespace. All of that will have their own clone and share syscalls. Then we go into, and it's quite fast. So this one is not what is going to take time. Then we have everything around identity and privilege. So this is where you will find things like setting the host name, writing to /proc, and also changing the user ID, the group ID, all these kind of things. With the corresponding syscalls, then file system and rootfs. This one is a bit slow. You're going to start seeing things like umount to unmount what is not needed for the container, pivot the root, which is kind of superpower cgroups, much more safer, right? All those kind of things. So depending on the number of mount and the file system type, this can also cause some delay, right? Then you have the creation of cgroups, which is just creating directory and opening file, writing ASCII, characters into that. And then finally, you have the big switch, which is essentially switching to your entry point to run your container. So, but again, all of that is not monitored in Kubernetes, right? So if we want to monitor that, using eBPF, again, this is how I created this custom resource called a pod birth certificate, where you can simply, again, as opposed to Prometheus or Metrics API, which is much more of a pull-in mechanism. The good thing with eBPF or BPF trace for the scripting mechanism is that it's event-based. So it's going to start just doing things as you create the probes. So you can count, you can measure, you can do different things. As a result of that, you will never miss anything in your workloads and in the kernel. So in that particular instance here, I'm not sure though I code up all the syscalls, but actually there's a lot more. The point is there's a lot more happening that was I was saying, right? So 84/7 syscalls just to create a container. And the total duration, so this is great about eBPF, is that you can be super precise. So imagine if you, at some point, you want to go very deep into troubleshooting, this is a super useful tool, because now it's not hidden into some sort of odometer where you have to establish a rate and where it's aggregated and all those kind of things. So it's direct and it's event-driven, right? So there's no sort of information that will be hidden. So for troubleshooting, it's great. For long-term, dashboard type of things, maybe it's not so great. So here again, I've monitored a couple of very important milestone, like a fork with the different details, and the timestamp. So if we see like 0, it probably means that it's because it's counting in microsecond, right? So that's to give you an idea of what we could do with that. So basically now I'll just mirror the screen. So let's try to do exactly that. So here, this is my environment. Let's maybe make it a bit bigger, as you see. So I've got my kernel gossip namespace where I have two things. I have a kernel gossip operator, which is responsible for the CRD. I'll go deeper in detail later on in terms of the architecture and how it works. But just for now, we have an operator and we have a daemon set here that is running all the BPF script. So now what I'm going to do, I want to create a new pod here. So if I just go into this workloads, I'm going to also trigger, I'm going to start also doing stress testing so that we can see some CPU throttling data. So it's just a nginx container. I'm just annotating it to signify to my solution or to my program that I want to monitor that particular container and filter, eBPF information. I have CPU and limit defined, container port, and there I just have a job to use DDoSify to load, to stress that particular container, right? So let's just apply this. So I should see, the service. Container running. So I should already have my custom resource here. We should see basically the same thing, one birth certificate. And so basically the same thing. So by using eBPF, again, my custom resource was created, and I have here all the details with the different timestamp, right? So solution is working, which is good. And now let's go back to the next part. So here you go. All right. So that was for the pod burst demo. So again, much more precise than just looking at some data you can find on the dashboard. If you need to troubleshoot, this is the type of things you would want to do as just as opposed to just using Prometheus or these kind of things. But again, when I said use eBPF to monitor CPU throttling information, in fact, you can also do it with Prometheus. All right. Now, the difference is that, again, this is not available. So the throttling is on the bottom and CPU usage on the top. Now, the big difference with the metrics server is that this value here, or this counter, or this metric here, is not directly available. It's only available via Kubelet and cAdvisor. We're going to be talking about cAdvisor a bit later. But this is not that something is not working or anything. This is a conscious decision for the metric server. Does not cover this type of things. So for that, again, you need Prometheus. But we're going to see that this sort of graphs with the CPU throttling doesn't exactly tell you, like over the course of 10 or 1 minute, 10 seconds or 1 minute, when was the exact latency during that period of time, right? It's kind of hidden within the range. So again, this is where if you need to correlate information between your application and what's happening, I don't know, maybe on the network or in your kernel with CPU throttling, this is the type of solution you will need, something like eBPF, not something that is a bit flattened from data scraping, right? Okay, so let's talk about cAdvisor, right? So we know that Prometheus directly scrapes detailed metrics from the advisor for long-term analysis. So cAdvisor originally was a different process. Now it's from Kubelet. Now it's directly, it's a library within the Kubelet, and it's simply exposed via HTTP, and this is how Prometheus can just pull the data, right? So why Prometheus doesn't directly pull data from the host, right? Just for security and standardization. So everything is going through HTTP into Kubelet, and Kubelet just happens to have all the cAdvisor library. So it really acts as a poster, periodically waking up to read the container cgroup accounting files for the kernel, so all the CPU stats and other information. And you can think about it as a nodometer for CPU pain. So I've used odometer, but in English I had to look for the term. It's just what you have on the car with the mileage, So it means just is always going to go up, right? Never down. And by default, CPU stat and all of that, I think it's 10 seconds for all those cgroups values. And it's counting, so it's incrementing, all right? So again, it's all hidden into some sort of delay and aggregation and average. So just looking at the numbers tells you nothing about what's happening right now, only the total accumulated throttling since the container started. So to make sense of that particular counter, then Prometheus must calculate the rate over a time window. And it does that automatically when you configure Prometheus. So you don't have to specify, OK, this is the counter, please divide it by 10 seconds. It does that automatically with the rate function. But in the end, this gives you a smooth out sort of average. We're still hiding the real story. So, for example, a brutal 6-second, 100% throttle will eventually look like the same as a gentle 10% throttle if you consider a whole minute, which may not be relevant for your application, like performance degradation you just had, right? So you can think about it as really as a smoke detector. It's perfect for high-level dashboard, long-term trend analysis, and basic alerting. And it reliably tells you that there is a fire somewhere, but not in which room, right? If we want to make that particular analogy. So as opposed to this kind of concept, we have BPF trace or eBPF, right? So everyone familiar with eBPF. eBPF makes the Linux kernel programmable, lets you safely run custom code directly in the kernel space without changing the kernel itself. So BPF trace is a scripting, it's not really a language, but it's like the scripted version of eBPF C programming. You don't have to use C or anything. It's just scripted. And you can think about it as a stopwatch in the kernel. Instead of polling, BPF trace attaches tiny, so predefined safe programs, so they are the predefined probes, directly to the scheduler function that manage throttling. Right? So again, you just, by default, you can attach to it. I have an example just the next slide. So you can consider it as a raw event stream. You don't get an average, you get a rich stream of discrete events. Each event will contain the timestamp, the process ID, and like the time for which the throttling was happening until there's no throttling anymore. So it's really like very precise data. And of course, based on that, you can create actionable intelligence, like what I did. You can transform kernel signals into webhook, CRDs, and immediate responses, right? So you can do some sort of out-of-the-box automation because of Kubernetes as a platform. So here, as an example, this is a very simple BPF trace script where you're attaching here to that probe for the throttle CFS quota limits. It tells BPF trace to attach that probe in kernel event in the scheduler subsystem to exactly measure the CPU throttling. And the action here, this is, so we have at throttles com PID. So the comma PID, this is the key for the map. So the map, this is where you're going to store the data. So throttles here is our map. We have two key, com, which is the command, PID, which is, well, the PID. And what you want to store in that table, you just want to increment a counter for that specific key every time the probe fires. So it's how many times you experience throttling as an example. So it keeps going up. So yeah, there's no average, no delay. You get an immediate aggregated summary of the kernel truth. So, but still, there are some sort of hidden challenges with eBPF. So it's just for your knowledge. Most of them are already solved with modern, let's say, kernel. So typically, if you compile an eBPF program, you need kernel header, right? So you need, if you have an eBPF program, what is this? Okay. If you have an eBPF program, it means that for every kernel, for every different kernel, you need the right header, etc. But right now, there's different way to solve that problem. So this kind of write once, run everywhere type of solution with BTF, which is the BPF type format. And what is it going? Oh, because the Wi-Fi. Probably, I'm sorry, the Wi-Fi is a bit flaky. So the kernel ships with its own embedded blueprint, so you don't need this kernel headers. And there is also a way to pre-compile your eBPF program. So essentially what it means is, except if you use very old version of BPF trace, you may have to download the kernel headers, or if you use also very specific trace point. But it's not a major problem today. So that's the final architecture of what I wanted to show you today. So we have the daemon set. So the daemon set the kernel observer is two-part. So we have a Rust program. Its job is to load the BPF trace scripts. As the BPF trace scripts are triggered, they will collect information on specific containers. We'll just filter out this container using annotation, so we can, we can reduce the noise. And the Rust program is gonna parse those responses, like around observability and all the CPU throttling. Then we're gonna create a webhook to an operator, and that operator job is to reconcile what it gets with particular custom resources. So as I get information from the daemon set, it's going to create a custom resource with the information I want to display, right? So we have two ones. I've told you about the pod burst certificate and the kernel whispers, which is essentially combining all the CPU throttling information for a particular container, right? So it's just adhering to, it's a bit of an anti-pattern, right? So we're not creating the custom resource by hand to do something. Is kind of the opposite, where we are getting information, but we need a Kubernetes native way of just ingesting that particular information. So let's go a quick demo of that one. I've already launched the stress, so I'm just going to show you just the so normally I should see, completed here, the job with the CPU stress. If I go back to my CRD, so what it looks like. So it's exactly what I've showed you at the beginning. So now, of course, we get the CPU limit request usage, but we also get the main part, which is the throttle percent, by looking at every PID that experience CPU throttling using those eBPF probes. So it's a very precise number. And then I can obviously derive a couple of things, mainly, again, the CPU demand, because this is, if CPU demand is superior to CPU limit or request, it means that we have a problem. That's a simple way to calculate that we have effectively a problem. But from a metrics perspective, the metrics API still think it's okay with 95% usage, which means like your workload is well sized and it's healthy, but in reality, it's not, right? So let's go back to, all right. So just last but not least, can I just, okay. A couple of more information. So I've mentioned a couple of things. So let me take this. So PSI, everyone is familiar with this already a little bit? So pressure stored information. It's been alpha since 1.27, I believe. Now it's beta. It's essentially a kernel native pressure gauge. It uses direct signal from the Linux kernel to quantify contention for CPU, memory, and IOs. And the idea is to measure wasted time per task. Right? So not just utilization. So instead of asking, is the CPU 100% busy? So PSI will ask something like, how much time are tasks spending stalled, waiting for the CPU? So, and the good thing is that it's exposed, again, as a cumulative counter, and metrics are available directly in /proc/pressure as a total stalled time in microsecond. But the good thing is that these metrics are ready to scrape. Again, not via the metric server, but you can collect and visualize by the standard Kubernetes metrics cAdvisor endpoint with the Prometheus adapter, right? So it will give you also an idea of pressure and CPU throttling, all those kind of things. But again, pool mechanism, not as precise as with eBPF. So just to finish off, key takeaways. So today we're seeing the difference between the metrics APIs. Sorry again, I should just shut off the Wi-Fi. The difference between metrics API, the dashboard, great for trends. If you need signals to correlate your application, start using eBPF. You can start using, of course, there's a lot of tools, Falco for security and visibility, Hubble from Isovalent and Cilium, all those kind of things. But sometimes you may need something very particular to your needs. In that particular case, hopefully, I gave you some ideas with CRDs, using operators, using BPF trace. You can solve some problems with that. So two perspectives, granularity, metrics versus Kernel events. And just to final point again, to hook the marketing side. If you guys want to know more about resources and scale up, this is exactly what we are doing. We don't scale blindly with like HPA, VPA, with that relies on the metrics server, right? So we rely on many more information, much more context. So check us out. Thank you.
I haven't seen so the CRDs that you just showed are part of an open source project, or
it's just me tinkering around myself. Like, it's in progress. There are stuff that doesn't work super well, but as I said, I'm a tinkerer. So, but yeah, if people are interested to build this kind of stuff, I'm more than happy to share the code.
Now you all know what to do. Right. Okay.
Question. So let's
jump to this.
Observation data and kernel with respect being rather in status. Yes, actually, I've put like recommendation in status. But yeah, you can have both, I guess, at some point. But yeah, if it's something dynamic you want to do, yeah, probably status is the best option, right?
In addition to the report style CRDs, are there plans to integrate with OpenTelemetry?
Well, I have plans now.
Plenty, I guess. Yeah.
Yeah. I mean, this wouldn't be too difficult, right? This is pretty standard. But again, once we have the metrics, once we have the value, we can do. I can do because it's a royal we,
Yeah. We as myself can do.
Yeah,
something.
we as myself. Yeah, OpenTelemetry. Yeah, of course. Once you start doing these kind of things, if you want to centralize everything and kind of standardize, of course, you would use something like Hotel. Yeah. Okay. BPF trace. Like anything with BPF, I would assume between 3 to 4 person CPU, one time sort of overhead. Like any eBPF programs, there's always a trade-off. And Henrik said, I know he is testing a lot of eBPF tools and measuring all of that.
Have you looked at Inspector Gadget?
Inspector Gadget, yeah, exactly. Yeah. Share it, okay.
Do it.
Yeah, I just need to, it's like this thing, you have an ugly baby, you don't want to show it to others until it's nice, or...
Just drop it somewhere on
Just
GitHub.
drop it.
I mean, a lot of people would be happy to play with it. Any one last question in the audience, perhaps?
Oh, that's my linking profile. Actually, it's not there.
3.
Yeah, anyway.
2. 1. Okay. Thanks a lot for your time.
All right, thanks you guys.
A big round of applause.
Let's connect
for
on
our
LinkedIn
speaker,
if you
please.
want. Or Strava.
From ContainerDays Hamburg, this video is proudly presented by ContainerDays.